Hi, this lesson is about curve sketching, and we'll be finding characteristics to sketch an accurate curve by using some skills that you learned in algebra and pre-calculus, as well as some calculus skills. So here's a review of some of the things that you already know and have recently learned. And so one of the characteristics you'd like to know about a curve is what its domain is. The domain is the set of all possible values of x. Your x-intercepts and your y-intercepts will be points you would want to find. Sometimes they exist, sometimes they do not. So x-intercepts, you find them by letting y equal 0 and solving the equation, and y-intercepts you find by replacing the x with 0. Symmetry. So we're going to focus on even and odd symmetry, although there's other types of symmetry. So even symmetry means it's symmetric about the y-axis. And you determine that by solving this equation or determining if it's true on the right and the left. If the original function f of x is equal to f of negative x, meaning all of the x's get replaced with a negative x, left side equals the right side, then you can say it's symmetric about the y-axis. And odd symmetry means that it is symmetric about the origin. So in that case, you would want to determine if f of negative x equals negative f of x, or, and I usually do this, you can also check if the original function equals the opposite sign of f of negative x. So if you can determine if the left and the right side are the same, then you can safely say that it is odd. So asymptotes. Not all functions have asymptotes, but if they exist, you'd want to identify them because then they would be represented on the graph with dotted lines to help you guide your graph. So vertical asymptotes are values of x that result in division by 0. And that can be shown by taking the limit as x approaches a from either the left or the right. And if f of x goes to plus or minus infinity, then x equal to a would be considered a vertical asymptote. Horizontal asymptotes are found by taking the limit as x approaches either infinity or negative infinity. And if that limit equals a finite value, which we're calling L, then you can say that y equal to L is a horizontal asymptote. Okay, so now we're on the calculus part. Intervals where the function is increasing and decreasing. Well, we figure that out by determining where is your derivative greater than 0. If your derivative is greater than 0, then the function f is increasing. When your derivative is less than 0, then your function f is decreasing. So along the same lines, we use the first derivative to identify extreme values, so maximums or minimums. And we do that by taking the first derivative, setting it equal to 0. Those solutions are called critical values, and then we test them to see if they are, we use the first derivative test in order to determine if they are a maximum, a minimum, or neither, which could also occur. Points of inflection and concavity, well, that's when we use our second derivative. We take the second derivative, set it equal to 0. Those solutions give you possible inflection points if solutions exist. And those solutions also allow us to then figure out what our test values are in order to determine concavity. So when your second derivative is positive, the graph is concave up. When your second derivative is negative, the graph is concave down. So with all of the information I just reviewed, you would get a pretty decent sketch of what the curve should look like. All right, so we have several examples. The first two are polynomials. So we want to sketch the graph of f of x equal to x cubed minus 9x. So from pre-calc, you probably know that this is an odd function, an odd polynomial function with a leading coefficient that's positive, which means that your graph should be dropping to the left and rising to the right. And then it does some other things in between. But in the end, that's what it should look like. It should be dropping left and rising right. So our domain for any polynomial function will always be all real numbers, so no restrictions. X-intercepts. That's when you set the function equal to 0. This function is factorable, so factor out an x, leaving you with x times x squared minus 9, which gives you 3 solutions, 0 and plus or minus 3. Remember, those numbers represent your x-intercepts, which are here in the green box, negative 3, 0, 0, 0, and 3, 0. So throughout this lesson, anything that I would want to remember in order to help me sketch the graph will be enclosed in this bright green box. Your y-intercept, that's when x is 0. Well, that's also 0, 0. That point is already identified above, so not necessary to remember that one. It's already in the above step. Symmetry. So let's check if this is even. Remember, to check if it's even, you're determining if f of x equals f of negative x. So the work is here on the next couple of lines. So when you simplify the right side, you end up with the right side being equal to negative x cubed plus 9x. That is not the same as what the original function is, and therefore you can safely say that this is not an even function, meaning it's not symmetric about the y-axis. Well, now let's check if it's odd. To check if it's odd, you have to determine if f of x equals negative f of negative x. So the work is here, starting at this line. And when you simplify the right side, you get that the left and the right side are in fact the same. And since they are equal, you can safely say that it is symmetric about the origin. It's an odd function. Okay, so let's move on. So I want to find asymptotes. Well, with polynomials, you're not going to be able to find asymptotes. There will be no line that the graph approaches and doesn't touch. So with polynomials, just state there's no asymptote. So you can move on. No asymptotes. F prime. All right. F prime is equal to 3x squared minus 9. Remember, our original function, f of x, was x cubed minus 9x. So you're just using power rule to find f prime. Set that equal to 0. Solve it. I used square root method, and you get that x is equal to plus or minus root 3. Those are my critical points, and they are potential maximum and minimum values. So here, I use my number line to help me keep track of what's going on to the left and right of those critical points. So you put negative root 3 and root 3 on your number line. And then you pick test values. Doesn't really matter what your test values are, as long as they are within the interval that's indicated. So when I pick something less than negative root 3, well, negative root 3 is about negative 1.7. So as long as you pick something like negative 2 or negative 3 or anything below that and plug it into your first derivative, then you can determine the sign. So anything to the left of negative root 3 results in a positive first derivative, which means that your graph is increasing. That's why I have this arrow here going upward, because it's increasing. Then you pick a number between negative root 3 and root 3, so the easiest choice is 0. Again, plug it into your first derivative, you get a negative result, which means that f of x is decreasing. And again, if you pick something greater than root 3, like 2, 3, 4, 10, it doesn't matter, you'll get a positive result. Graph is increasing. So it's going up, then back down, then up again. So in summary, I have that the graph is increasing from negative infinity to negative root 3, and then from root 3 to infinity. And it's decreasing from negative root 3 to root 3. So your intervals of increasing and decreasing should always be open, never closed intervals. That also means that I have extreme values. So if your graph is increasing then decreasing, that means I have a maximum at negative root 3. And since I need to know what the coordinates are associated with that, that means you're going to plug in negative root 3 into your original equation, which is right here on the right, x cubed minus 9x. So the work is found here. Plug in negative root 3, and you get a result of 6 root 3. So negative root 3, 6 root 3 is a maximum value. But since I need to plot this eventually, I'm going to need to know what these are approximately. So negative root 3 is about negative 1.73, and 6 root 3 is about 10.39. All right, we do the same work for positive root 3. Positive root 3 is a minimum because before positive root 3, the graph is decreasing, and then after root 3, it's increasing, meaning I have a minimum value. And if you do the same work, you get that root 3, negative 6 root 3 is your minimum point. All right, so we move on to the second derivative. Remember, second derivative will allow us to find concavity and inflection points if they exist. So my second derivative is 6x. Set that equal to 0, and you get that 0 is a potential inflection point. So this time on your number line, you just put 0 on there because that was the solution above. And then we pick a test point to the left and right of 0, and we plug it into your second derivative. If you pick something less than 0, second derivative is negative. A negative second derivative means that your graph is concave down, which is why I have this concave down looking shape in that interval. And if you plug in something greater than 0, it is concave up, right? So this is just a little tool to keep us organized. So in summary, it's concave down from negative infinity to 0, concave up from 0 to infinity. And because there's a change in sign from negative to positive, I can safely say that 0, 0 is an inflection point. So now let's put this all together. Everything that's in a green box needs to be used in order to come up with our sketch. So I did that over here on the right. Just to remind you, I had intercepts at negative 3, at 0, and at 3. I had a local max at this, if you recall, this was negative root 3, 6 root 3. And I had a local min at positive root 3, 6 root 3. So we found that earlier. And we have an inflection point here at the origin. So it's not only an intercept, but it's also an inflection point. So if I just keep in mind what my first and second derivative were telling me, remember it said it was increasing from negative infinity to negative root 3. Well, we see that here. It is increasing from negative infinity to negative root 3, and it's also increasing from root 3 to infinity. So this is the part that's increasing, but it's decreasing in between negative root 3 and root 3, so it's going downward. So it matches up with what we were expecting in terms of increasing and decreasing. And remember, concavity, got rid of my line. For concavity, it was concave down from negative infinity to 0, and it's concave up from 0 to infinity. So that's also obvious on this graph. Okay. By the way, this is the number 10. Not sure if that's clear. All right, so let's move on to another function, another polynomial. I want to sketch the graph of y equals x to the fourth plus 4x cubed. And again, if you remember your pre-calc, this time I have an even degree, leading coefficient that's positive. So to the left, the graph should be going upward, and to the right, the graph should be going upward. And in between, I'll be doing other things, but that's just something that's discussed in previous courses. So your domain, again, because it's a polynomial, is all real numbers. X-intercept, set the function equal to 0, factor, you get 2 x-intercepts at the origin and at negative 4, 0. Y-intercept is also at the origin. Okay, symmetry. So we check for even. And so here, again, if you check if x to the fourth plus 4x cubed equals negative x raised to the fourth power plus 4 times negative x raised to the third power, you'll find that the left side and the right side are not equal, so therefore this is not even. If you do the same thing for odd, the only difference is that you take the opposite sign on the right side of all the work you did. You also get that they are not equal, and therefore there's no symmetry. Okay, so asymptotes. There are no asymptotes, again, because this is a polynomial function. First derivative. Take your derivative. So as a reminder, let me just remind you what the function was. So it was x to the fourth plus 4x cubed. Okay, so when I take my first derivative, right here, you get it's 4x cubed plus 12x squared. Set that equal to 0. Again, this is factorable. And you get two solutions at 0 and -3. So remember, these are potential maxes and mins. These are your critical points, -3 and 0. So now we have to check it, do our first derivative test. So pick something less than -3, plug it into your first derivative. Now the easiest place to determine sign is here where they're factored. Remember, we don't really care what the answer is. We just want to know what the sign is. So if I pick something like -4 and plug it in where it indicated with the arrow, you get a negative result. That means the graph is decreasing. If you pick something between -3 and 0, you get a positive result. But you also get a positive result when you plug in something greater than 0. So it's decreasing from -infinity to -3, but it's increasing from -3 to 0. It doesn't look like anything special is happening at 0 in terms of extreme values. But that doesn't mean that 0 won't be important. So we'll move on and see what happens when we move on to the second derivative in a minute or two. So -3 is a critical point that represents a minimum value. And so, when x is -3, f of -3 is equal to -27. So -3, -27 is a point on the graph. So whenever you're finding points, maxes and mins, and inflection points, make sure that you're always substituting back into the original function. All right, so now we take the second derivative. Second derivative is 12x squared plus 24x. So factoring, you can factor out a 12x times x plus 2, x is 0, x is equal to -2. Those are your potential inflection points. So again, we put those two numbers on the number line. Always put them in numerical order, so -2 goes first, then 0. If you pick something less than -2, plug it into your second derivative, you get a positive result. Pick something between -2 and 0, you get a negative result, and something greater than 0 will give you another positive. So it is concave up from -infinity to -2, then from 0 to infinity, and it's concave down in between at -2 and 0. So therefore, -2 and 0 are inflection points because there is a change in sign from positive to negative and then negative to positive. So when x is -2, your y or your f of x is -16. And when x is 0, your y is 0. So it turns out that 0, 0 is an important point on this graph. It's actually an inflection point. All right, so we need to put all of this together in a graph, which is here on the right. So I really like this example because it's an example of something that if you only found the first derivative, you probably wouldn't get an accurate picture because concavity is a little tricky here. So I plotted my x-intercepts. I have -4, 0, and 0, 0. I also plotted our absolute and local minimum. And so as a reminder, the minimum was at -3, -27. So that's what you see here. And then remember, we had two inflection points at -2, -16. Those are the points that you see here in black, and at 0, 0. So the first derivative said that the graph is decreasing from -infinity to -3. and then it's increasing from -3 to infinity. So that's something that we see here. But it's concave up from -infinity to -2, and then it has, and then it's concave down from -2 to 0. And so let me just show this because it's kind of subtle. This is the concave down part of the graph, and then it transitions back to concave up. Okay, so now we'll move on to a rational function. So I have f of x equals x squared over x squared plus 3. Here the domain is also all real numbers. With rational functions, you really have to be careful because oftentimes there are restrictions to the domain. But if I took my denominator and set it equal to 0, that's the work you see right here, you actually get an imaginary solution. And so that means there is no real number that would result in division by 0. So anything we're doing regarding curve sketching will have to do with the real number system. You won't be plotting imaginary numbers on an XY plane. So that wouldn't make sense here. So there's no restrictions to domain. X-intercepts. So we take x squared over x squared plus 3, set it equal to 0. Whenever you're solving rational equations you equal to 0, you want to just solve the numerator. And so x squared is equal to 0, which gives me only one solution here. X is 0. And when x is 0, if you plug it into the original function, y is also 0. So again, I have an x and a y-intercept at 0, 0, and there's only one point. Symmetry. All right, so if we check this for even, it means that you're replacing all of your x's with -x here on the right. Let me just change the color for this problem so it's easier to follow what I'm doing. We'll make it blue. All right, so here, replace your x's with -x. Left side equals the right side, so this function is even. If it's even, you don't need to check if it's odd. It wouldn't be both even and odd and still be a function. Asymptotes. So there's no vertical asymptote because there's no division by 0 here. We already established that when we discussed the domain. So that's taken care of here. Horizontal asymptote, that's when you take your limit as x approaches plus or minus infinity. Now, we'll get the same result whether we do positive infinity or negative infinity, so I just have the work for positive infinity. So if you consider how to simplify this limit algebraically, the trick is to multiply the top and the bottom of the rational function by the reciprocal of the term in the denominator with the highest exponent. So I'm going to multiply top and bottom by 1 over x squared. And when you simplify, you get 1 over 1 plus 3 over x squared. And as x approaches infinity, 3 over x squared goes to 0. So your horizontal asymptote is the line y equals 1. But you could also do this with L'Hopital's rule. That's the work that you see here. So that's something that we learned recently. So let me just move this over a little bit. So if I take the limit as x approaches infinity of x squared over x squared plus 3, that's indeterminate form infinity over infinity, which means L'Hopital's rule applies. I apply L'Hopital's rule on the next line. You get 2x over 2x. That's something you can simplify algebraically. The 2x's cancel, and you get the same result of 1. And again, that is your horizontal asymptote. All right. Derivatives. So remember, first derivative allows you to find intervals of increasing and decreasing, maximums and minimums. So because I have my original function is a quotient, I'm going to use quotient rule. And so the work is here on the side, and the actual derivative applying the quotient rule is here on the left. So remember, it's gf prime minus fg prime all over g squared. When you simplify, you get that the derivative is 6x over x squared plus 3 squared. So as I mentioned earlier, when you have a rational equation and you set it equal to 0, you're solving the numerator. So here you see that 6x equals 0, which gives you a result of 0. And so 0 is our potential max or min, our critical point. So that's the only value that you show on the number line right here. So then we pick test points. And when you pick test points, you're plugging it into your first derivative, which is here. And when you do, something less than 0 will give you a negative result. Something greater than 0 will give you a positive result. And so in summary, the graph is decreasing from negative infinity to 0, and it's increasing from 0 to infinity. Okay, so now that means that 0 is an extreme value, and it's actually a minimum because the graph is decreasing then increasing. And when x is 0, your y is 0, and so here's your minimum value. There's no maximum. Now, to find y double prime, or the second derivative, you are basing that off of your first derivative here, again using quotient rule. So again, the work is here. Let's see if this draws properly. Work is here. We plug in to the quotient rule formula, and when you simplify, you end up with a derivative of, somehow this got erased, negative x squared plus 18 over x squared plus 3 to the third power. So as I mentioned before, you're going to want to solve it here on the right. So we have negative 18x squared plus 18 equals 0. So using square root method, you get that x is equal to plus or minus 1. So those are your two potential inflection points. And so now we have to pick test points to the left of negative 1, between negative 1 and 1, and to the right of 1. And we are plugging in here to determine our sign. So if you pick something less than negative 1, you get a negative result. If you pick something between negative 1 and 1, you get a positive result. And remember, positive means it's concave up. And if you pick something greater than 1, you get another negative result, and that is concave down. So in summary, it is concave down from negative infinity to negative 1, and then from 1 to infinity, and it's concave up in between negative 1 and 1. Since I seem to have lost some of this, let me just put my green box around this as well, because this will be important to help us graph this later on. All right, but that also means that negative 1 and 1 are inflection points because there is a change in sign from negative to positive in terms of concavity, and then positive to negative. So if you plug in negative 1 into your original function, you have an inflection point at negative 1/4. Plug in 1, you have an inflection point at 1 and 1/4. All right, so all of this information has to be put together in a sketch, which is here on the right. Let me just move this over. All right, so remember there was only one intercept here at the origin, right here. That was your x and y intercept. We also had a horizontal asymptote at y equal to 1. That's this dotted green horizontal line. And then we had our two inflection points at 1 and 1/4 and negative 1 and 1/4. All right, then we also found that the graph is decreasing from negative infinity to 0 and then increasing from 0 to infinity. So let's see if we see that. It's decreasing from negative infinity to 0, increasing from 0 to infinity. That's true. Now let's talk about concavity. Remember, it's concave down from negative infinity to negative 1, and also from 1 to infinity, but it's concave up in between negative 1 and 1. So concave down, this is the concave up part. I'll draw it in green, go over the blue. This is the concave up part, and then it goes concave down again. So everything matches up with what we expected based on the information we found. All right, so now we move on to a radical. I have y equals x square root of 5 minus x. So just like rationals with radicals, you're going to want to check to make sure what your domain is. Inside of a radical, you do not want a negative inside of a square root. Again, because no imaginary numbers in this curve sketching. So the domain that will allow us to always get a real number result is from negative infinity to 5. Anything greater than 5 would give us a negative result inside of this radical. So we need to keep that in mind. X-intercept. Remember, that's when you set the equation equal to 0. Here, to solve it, I squared both sides. So you get x squared times 5 minus x equals 0. You get two solutions, 0 and 5. So 0, 0, 5, 0 are my x-intercepts, and 0, 0 is also a y-intercept. So because of this restriction on domain, very unlikely there's going to be any kind of symmetry, but we'll show the work anyway. It's good practice. So if you check for even, left side and right side are not the same. If you check for odd, again, left side and right side are not the same. There is no symmetry that's going to help us sketch this graph. So here, there are no asymptotes. There's nothing that will result in division by 0. And I'll show you the work for checking for a horizontal asymptote. Remember, with horizontal asymptotes, you're checking the limit as x approaches either positive or negative infinity. Well, positive infinity wouldn't make sense because remember, your domain is from negative infinity to 5. So I'm going to check the limit as x approaches negative infinity. Well, as x approaches negative infinity, this x here goes to negative infinity. And this one will be this inside part, because it will be minus negative infinity. Well, this goes to infinity. So negative infinity times positive infinity goes to negative infinity. So if you don't get a finite result, you're not going to have a horizontal asymptote. So no asymptotes in this graph. All right, so now we need to find our first derivative. So x times 5 minus x to the 1/2, that's our original function. I just wrote it without the radicals so that I can easily take the derivative. This is a product, so here's the work on the side for product rule. So f is x, f prime is 1, g is 5 minus x to the 1/2. G prime, you have to use chain rule. So it's 1/2 5 minus x to the negative 1/2. And then don't forget the derivative of the inner function, this one here. Well, that's negative 1. And so my G prime is negative 1 over 2 root 5 minus x. All right, so we plug that in here into the product rule. So I did f g prime plus g f prime. You end up with two rational expressions with a different denominator. We get a common denominator, which is 2 root 5 minus x on this line here. And so when you combine like terms in the numerator, your first derivative is negative 3x plus 10 over 2 root 5 minus x. All right, so we solve this, and again, we're just solving the numerator. Negative 3x plus 10 equals 0, that's linear. You get that x is 10/3. 10/3 is 3 1/3. Now, when we do our testing, our first derivative test, remember that there's a restriction on domain. It goes only up to 5, so make sure you don't show all real numbers here because you can't just pick anything you want in terms of test points. So to the left of 10/3 or 3 1/3, there you can pick any number. So if I pick something less than 3 1/3, like 0, for example, I'll get a positive result, which means the graph is increasing. And if I pick something between 3 1/3 and 5, such as 4, and plug it into my first derivative right here, then you will get a negative result, and so it's decreasing. So in summary, it's increasing from negative infinity to 10/3, and it's decreasing from 10/3 to 5. That means I have a maximum value at 10/3 and f of 10/3. And if you plug in 10/3 into your original function, do the simplifying, there'll be some rationalization that you have to do, you get that your maximum value is at 10/3, 10 root 15 over 9. And for the purposes of graphing, you're going to want to know what that is approximately. It's about 3.3 and 4.3. So we'll use that later. And now we move on to finding the second derivative. All right. So second derivative, we have to apply quotient rule to my first derivative, which is right here. The work for quotient rule is here in this blue bubble. So numerator is your f, denominator is your g. Again, to find g prime, you have to apply chain rule. So the second derivative plugged into quotient rule is right here. So I have y double prime is 5 minus x to the 1/2 times -3 minus -3x plus 10 times -1 over 5 minus x to the 1/2. So from that line to this line, this is in the wrong spot. Let me put it right here. This is where number 6 starts. So y double prime here, I'm rewriting this to show you that I have two separate rational expressions in the numerator with different denominators. The common denominator is root 5 minus x. So from this line to this one right here, we're getting a common denominator. So I'm left with -6 times 5 minus x because this radical goes away when you multiply by root 5 minus x, minus 3x plus 10. In the next line, we distribute the -6 across, leaving us with this expression, and then combine like terms. So you get y double prime is 3x minus 20 over your denominator, which is 4 times 5 minus x to the 3/2. So that happened because we combined this 5 minus x with this one here. So that's where the 3/2 power comes from. All right, so we take the numerator, set it equal to 0, and we get that x is 6 2/3. But again, you have to remember, what's your domain? Your domain goes from 0 to 5. So this is outside of the domain. That means there is no inflection point. But that doesn't mean you can't check your concavity. I still have to check if it's concave up or down. And so pick any value to the left of 5, plug it into your second derivative, and no matter what you pick, you'll get a negative result, which means that the graph is always concave down from -infinity to 5. All right, so all that information has to be put together. There isn't a whole lot of things for us to plot. Remember, there were only two intercepts that was here, this one and this one, at 0, 0, and 5, 0. There was only one maximum value. It's both an absolute and a local max, and that was at right here, about 3.3 and 4.3. And the graph was increasing, then decreasing. That's seen right here. Increasing, then decreasing, which this graph shows that. And it's always concave down. So that's all there is to it. All right, we have one more. This one has a natural log in it. We want to sketch the graph of f of x equal to x minus ln of x. Here the domain is only positive real numbers, and that's because ln of x has restrictions. Your ln of x function all by itself looks like this. This point here is 1, by the way. And so the closer you get to 0, this is approaching -infinity, but it's not defined at 0 and it's not defined at any negative number. So your domain is basically dictated by ln of x here. X-intercepts. So we have x minus ln of x equals 0. So if you tried doing this, you can do e to both sides, try to solve this equation. You just end up going in circles. There's no solution to this at all. So you have no x-intercepts, and you also have no y-intercept, because remember, x equal to 0 is not in the domain. Okay, so far, we don't have a whole lot to go on other than that we know that the domain is only positive numbers, but we don't have any points to plot so far. Now we're going to check for symmetry. Again, because of this domain restriction, this is not going to be symmetric, but we'll show the work here. So we check for even, left side does not equal the right side, so it's not even. Check for odd, left side does not equal the right side, definitely no symmetry here. Asymptotes. So let's check for vertical asymptotes. The only possible place where there could be a vertical asymptote is at 0. Because remember, it's only defined from 0 to infinity, but not including 0. So let's see what this looks like. If I take my limit as x approaches 0 from the right of x minus ln of x, well, by direct substitution, x is just 0, so that's what you see here. But as I mentioned before, as x gets closer and closer to 0 on the right, ln of x goes to negative infinity. So that's what we were talking about up here. So as x gets closer to 0 on the right, this here gets closer to negative infinity. Okay, so that means that that the limit of 0 minus negative infinity, it means that this limit is going towards infinity. All that's telling me is that this graph is getting larger and larger as your values of x get closer to 0. So that means that x equal to 0 is a vertical asymptote. All right, horizontal asymptote. Okay, so let's talk about this conceptually. It's very unlikely that there would be a horizontal asymptote here, and let me explain why. I have the limit as x approaches infinity of x minus ln of x. X grows much faster than ln of x. So if you remember your graphs, y equal to x would look like this, and y equal to ln of x goes like this. So the larger your x values are, the line will be much larger. It will outperform it. The values of x will grow much faster than your ln of x values. So that's why I would say, if I were guessing, there isn't going to be a finite result here. But we can prove it, and we're going to use L'Hopital's rule, because this is indefinite form of infinity minus infinity. All right, so the tricky part is figuring out how to rewrite this in terms of a quotient. So remember, x can get rewritten as ln of e to the x. Remember, ln and e are inverse functions, so ln of e to the x equals x. These are equivalent to each other. Okay, by writing that as an ln function, I can use my log properties to rewrite ln e to the x minus ln of x as ln of e to the x over x. Well, ln of e to the x over x is not a quotient. It's ln of a quotient. So for the time being, we're going to ignore ln, and we're only going to evaluate the limit of the quotient. The limit as x approaches infinity of e to the x over x. This is also indeterminate form of infinity over infinity, which means we can apply L'Hopital's rule. When I apply L'Hopital's rule on the next line, remember I use that little h to indicate that I'm using L'Hopital's rule. You take the derivative of the numerator and the denominator, so I get e to the x over 1. As x approaches infinity, e to the x grows very quickly. 1 is a constant, so this is no longer L'Hopital's rule. So this limit is approaching infinity. If the limit of the quotient is approaching infinity, then ln of infinity will also be infinity, and therefore there is no horizontal asymptote. So we only have a vertical asymptote to keep track of. All right, first derivative. So remember, I'll just remind you here, f of x is x minus ln of x. So my first derivative will be 1 minus 1 over x. Remember, the derivative of ln of x is 1 over x. We add 1 over x to both sides, and then we cross multiply, and you get one critical point at 0. Okay, so I'm sorry, at 1. So that's the number that you put on your number line. But remember, this number line doesn't go on and on forever in both directions. Your restriction there's a restriction on domain starting at 0, and it's not defined at 0, so I'm showing that with this. All right, so when I pick a number less than 1, you have to pick a number between 0 and 1. So something like a half would be fine. And if you plug that in, 1 minus 1 over a half, well, that's the same as 1 minus 2. And so that gives you a negative result, means that your function is decreasing. And if you pick something greater than 1, like 2, 1 minus a half is positive, and so it's increasing. So this is the summary of what we expect in terms of decreasing and increasing. Now we move on to maxes and mins. So when x is 1, f of 1 is 1. And again, when you're finding maxes and mins, you're plugging it back into the original function. So when x is 1, you have 1 minus ln of 1. Remember that ln of 1 equals 0. So we have a point, a minimum at 1, 1. And now we're ready to find the second derivative. So second derivative is based off of your first derivative. I rewrote my first derivative without the fraction, so that's 1 minus x to the negative 1. So when you take the second derivative, power rule, you get x to the negative 2. Set that equal to 0. Well, 1 over x squared will never equal 0. That's a rational function with a constant in the numerator, and your only variable is in the denominator, so that's actually impossible for that to equal 0. So therefore, that means there's no inflection point. But similar to the previous example, that doesn't mean you can't check for concavity. Remember, your domain is from 0 to infinity. So as long as you pick any number in the domain, plug it into your second derivative, which is here, then you can find your concavity. So no matter what you pick, if you do 1 over that value squared, you're going to get a positive result, which means your function is always concave up. So it's concave up from 0 to infinity. All right, so we have to keep track of all of this. It's always concave up. We have a minimum at 1, 1. We had no intercepts, and we had an asymptote at x equal to 0, and no symmetry, and where's my increasing, decreasing? And it is decreasing from negative infinity to 1 and increasing from 1 to infinity. All right, so here's our graph. It's decreasing from negative infinity to 1. It's increasing from 1 to infinity. We have an absolute and a local minimum at 1, 1. And the line x equal to 0, which is your y-axis, is your vertical asymptote that's indicated here with a dark blue line, and it's always concave up. So that's a lot of different examples for you to consider when you're working on the homework for this. So hopefully this helped. If you have any questions, just let me know.